Hello and welcome to this video about finding the square roots of matrices without using any eigenvectors. This can be done by finding a polynomial that evaluates the square root of this matrix that has eigenvalues that are all different to each other. I wish to extend this method to Jordan canonical matrices, so we'll quickly prove it for matrices that are diagonalizable. We'll start with a matrix A, which will be filled with elements that are small subscripted a's, and will also be a square matrix, so it'll have behavior like a number. We'll be able to find its square root, cube root, and logarithm, because it is a ring object. We'll assume that A is diagonalizable, and that there is a change of basis matrix P, and also a diagonal matrix D, so that this formula is true, so A and D are similar. And this is what D looks like, with eigenvalues lambda1 to lambda n along its diagonal. Two or more of these eigenvalues may be equal, but just as long as it's a diagonal matrix. It is possible that no diagonal matrix D exists for matrix A. Then it's a non-diagonalizable matrix. So then it will be made up of Jordan blocks along its diagonal and superdiagonal. And so we'll say that A is Jordanizable, since every matrix is Jordanizable. So we can find a change of basis matrix P, and also a Jordan matrix J, so that this equation will be true. So A will be similar to a Jordan matrix if it isn't similar to a diagonal matrix. This is what a Jordan matrix can look like. It has at least 1, 1 in the superdiagonal, which I've circled here. The superdiagonal is the diagonal which is immediately above the main diagonal. So if A is diagonalizable, then we can find a polynomial function that can give us the square root of matrix A, according to the theorem which is similar to the Cayley-Hamilton theorem, but is a different theorem. So here's a quick sketchy proof of this theorem. We'll set this square root polynomial to have these coefficients here, and A0 will be multiplied by the identity matrix, so that it can add together with all of these other terms. And we'll create the polynomial so that when it is applied to an eigenvalue of this matrix A, then it gives us back the square root of this eigenvalue. And we'll do this by using interpolation. And so we'll suppose that these are all of the eigenvalues of A, and there are n plus 1 of them because there are n plus 1 coefficients in the polynomial to find. And all of them have this property, that when we apply this polynomial to each of these eigenvalues, then we get the square root of each of these eigenvalues. We can write it out in this more generalized form. So then we can expand out all of the polynomials to give us these equations. Then we can pack all of these equations up into this matrix vector equation, so that we can solve to get all of the coefficients of this polynomial. So this is what applying the polynomial to the diagonal matrix D looks like. It's like getting the square roots of all of these diagonal entries. And we can quickly show that when we apply this polynomial to the matrix A, then we get its square root too. We don't even have to have the primary square roots. We can have the negative square root of one or more of the eigenvalues too. And this quickly and visually proves the theorem. But it won't work if A has no diagonal matrix that it's similar to. So we'll have to modify this system of equations so that it can find the square root of a Jordan canonical matrix. And this is very helpful because every matrix is Jordanizable. That is, it's always similar to a Jordan canonical matrix if it isn't similar to a diagonal matrix. So we'll work on the most simple Jordan matrix possible first, the 2 by 2 Jordan matrix given here. These diagonal entries must be positive for this to work, although we could work with complex numbers if the diagonal entries are negative. We start with finding the polynomial that has this property, that it can return the square root of the eigenvalue of this matrix. We'll then get the derivative of both sides of this equation to get the next equation. And then we'll use these two equations to find the polynomial with this property. So these are the two equations that we'll be using. The second is gotten by taking the derivative of the first. And then we can pack it up into this equation and then solve it to get the coefficients A0 and A1. There is a reason why this works, and I'll do a sketchy proof of it later in another video. Now supposing that we have a large n by n matrix with one giant Jordan block that takes up the whole matrix, we'd be able to solve another larger matrix that contains this block with this method. We'll use the method of solving for derivatives to find the polynomial that gives us the square root of this matrix. So these are all of the derivatives of the polynomials that we wish to solve to find the polynomial, and we have to find all of the derivatives of the square root function as well. We'll have to pack all of these equations up into a large matrix to solve for all of the coefficients of this polynomial. So we'll look at the first equation. It looks like this. We can pack it up into this vector equation like this, taking out all of the coefficients of p into this column vector so that we can solve for them. And so this is the second equation, and it's already a bit more complicated. We'll have to expand out all of the derivatives. And expanding out all of the derivatives gives us this equation. And we can pack it up into this vector equation with the same column vector of coefficients a0 to an of the polynomial p. And so now we have the third equation. We have to get the second derivative of both sides. And so this is what the second derivative of both sides is. I'll assume that you understand how to do this. And we can pack it up into this matrix equation here. So I hope that you can start to see a pattern, that is, how we can make a matrix equation out of all of these equations as we get more and more derivatives. So this is how we can pack these equations up into a matrix equation, with each equation representing a row in this matrix and the answer matrix, and the column vector of coefficients remaining constant. So now to get an arbitrary ith equation for this polynomial, we'll have to get the ith derivative. I here stands for an indexing variable and not for the square root of -1. And getting the ith derivative gives us this equation, which is complicated but not hard to understand. And then we can pack this equation up into this vector equation. So the last equation would look like this, being the nth derivative of both sides of this equation. Getting the nth derivative of both sides gives us this equation, which is simple because it only contains one unknown variable, an. And so it can be packed up into this vector equation, which makes it look more complicated, but makes us able to pack all of these equations into one matrix equation. So this is the final matrix that we need to build, but we still need to figure out a way of finding each row of this matrix. We'll use a vector that contains all of the coefficients for each derivative of this polynomial p. We'll call this vector PV, which stands for polynomial vector. Now to calculate the next value of PV, the polynomial vector containing all of the coefficients of the polynomial, that will have to change if we have a Jordan block in the matrix. This is what the polynomial is for the first value in the block, or if it's an eigenvalue that occurs only once in the matrix. So for an arbitrary polynomial vector, we'll store it in an array like this. Then to get the polynomial that we want, we'll multiply it by a column vector of powers of x like this. We'll substitute the polynomial vector in here. So then we'll get this polynomial, which is what this polynomial vector represents. Now here's an example of how to differentiate a polynomial vector. We'll demonstrate it on this value of PV. We'll multiply every entry by its location in the array. The first entry is located at 0, and we're colouring it red because we're going to discard it. We'll evaluate all of the entries, and then we'll discard the first entry, which gives us this polynomial vector. So the first polynomial vector that we'll have is a list of 1s. We'll multiply every entry by its position in the vector. Its length is n, so its last value is multiplied by n. Then we'll evaluate all of the entries. And then finally we'll discard the first entry, which gives us a list of numbers in order from 1 to n. Now to differentiate this vector a second time, we'll multiply each entry by its location in the array. Then we'll evaluate each entry. And finally we'll discard the first entry, so as to give us this new list of numbers that's harder to describe, but that represents the second derivative of the polynomial at the top. Now to calculate the nth derivative of the square root function, I went into this in some detail on my video on how to find the square root of a Jordan canonical matrix. We'll quickly go through it again here. We'll write out this function as x to the power of a half, which makes it much easier to differentiate. So to get its first derivative, we'll multiply the expression by the indice, and then decrement the indice by 1, or subtract 1 from the indice of x, giving us a half times the reciprocal of the square root. We'll repeat this process for the second derivative. This minus half multiplies by the half that is already there, and the indice decreases to be minus 3 on 2. Simplifying it gives us this, although I'd like to write the coefficient as 1 divided by 2 squared, because I'd like you to see the pattern that is emerging. So we'll repeat this process for the third derivative. Simplifying this gives us 3 divided by 2 cubed. The minus signs cancel to give us a positive fraction. Then we'll get the fourth derivative, and then we'll write 5 times 3 in the numerator to observe this other pattern that's emerging. And then when we get the fifth derivative, we can see the pattern for the numerator, which is a series of odd numbers multiplied by each other in a long list. The sign of the fraction oscillates between positive and negative. Finally, we can get a formula for the ith derivative of the square root function. We'll have to calculate this iteratively and store it in a table. So let's look at the graph of the polynomial function that we've just created from the eigenvalues that we've coloured in pink, and compare it to the square root function coloured in blue. It only needs to be equal to the square root at the eigenvalues to give us the square root of this matrix, even though it may be horribly inaccurate at all other points. If an eigenvalue occurs twice for this matrix and forms a Jordan block in the Jordan canonical matrix that it's similar to, so it's not diagonalizable, then we need to make the derivative of this function equal at this point like this. For example, there may be 2 eigenvalues of 5. In this case, we'd need to make the derivatives of these functions equal at x is equal to 5 as well. So this is what the polynomial actually is if I calculate it for these 3 values, and it follows the square root function fairly accurately for this region from about 1.5 to 6. I especially made up these other functions to illustrate that the polynomial need only be true for the eigenvalues and can be wildly different everywhere else, although this function may be inaccurate for 3 or 4 significant figures. So now to start writing the code. I'll start with this function to check whether matrices A and E are equal. I'll use this to test whether the square root function works by square rooting the matrix and then squaring it again, and then seeing whether this matrix is equal to the original matrix that we started with. We'll set this variable equal to true and find an occasion to set it false. We'll set this return variable to be false if the 2 matrices have different dimensions. I put this in for consistency, since the matrices would have the same rows and columns according to this program. So we'll check all of the elements in these matrices to be equal. If one location has different values for this matrix, we'll set the return variable to be false. I've allowed the difference between each entry to be less than a millionth, and we'll return the return variable here. So now to make a square root table to find the nth derivative of the square root function, which we'll need to use to find the correct polynomial that gets the square root of a matrix. I've already discussed it in my video on the square root of a Jordan canonical matrix, but I'll go through it again here. We'll set all of the initial variables here, since it's an iterative process. And we'll calculate all of these variables as we go through the loop. They're shortened names, like fact stands for factorial. We'll make a loop to get all of the entries in a table that's n big. N could be 100 or 1,000. We'll plug all of these values into the table. Then we'll calculate the entries to go into the next part of the table. They follow the formulas that we've developed to find the nth derivative of the square root of 2 that we found earlier. And this is where it's different to the function that I've made to find the square root of a Jordan canonical matrix. I don't divide it by the factorial. I then lastly set these global variables storing the length of the table. So here's a function to create random Jordan blocks stored as a list of entries that can be made into a matrix later. This is good for testing the matrix. I'll declare the function here. This is a global variable that stores the dimension of the matrices that we're working with. Other functions like interpolate will access this variable. I'm going to jumble up a lot of numbers. I'll start with an ordered list of numbers from 1 to 100. So this is code to jumble these numbers up, which is a reverse of sorting. I've made up a video to explain how to jumble numbers up already. It works through the list jumbling up numbers one at a time in each position of the array. Now I'm going to put these numbers into the table. I'll set these variables here. I'm using a while loop, so I'll set I to be 0 here. I'm making a while loop which will terminate when the numbers of eigenvalues remaining are 0 or less. This array stores the eigenvalue in the matrix, which is equal to the diagonal value. We'll get a random value for the size of the Jordan block, which is 1 to 3. We'll store the size of the block and its location in the matrix in this array here. We'll calculate the number of diagonal elements that are left over here. We'll calculate the location of the next block here. This variable indexes each Jordan block in this matrix and not each diagonal element. Very possibly the last Jordan block will be too big, so we'll have to trim it to fit into this matrix here. And finally we'll store the number of Jordan blocks here. Now this is the function that will find the polynomial that we're after. We'll set this variable here to equal the size of the square matrices we're working with. This will be equal to the number of rows in the matrix that we'll solve to find the polynomial that we want. We'll set the dimensions of the augmented matrix that we want to solve, and these variables that will be used in the for loops. We'll set A equal to the 0 matrix to begin with. It's easier and faster to do it this way. IR will be used to store the index to each row in the matrix, which we'll have to store separately to the index of the Jordan blocks. We'll make a loop to construct a matrix from the Jordan blocks that we've created earlier. Then we'll get these values from the Jordan block table. We'll make a polynomial vector that we've described earlier. It's initially set to having all ones. We'll make up a loop to look at each row in the Jordan block and make the correct equation to place into the interpolation matrix. This variable represents x to the power of n, which represents each power of x in the interpolation matrix. Now we'll loop through each column in this matrix, but we're using rows in the for loop because we're not loading anything into the last column here. Now we'll load the powers of x into the row of the matrix here. We'll use the variable IR to store the row that we're working on. Now we'll increase the power of x as we work along the row. We'll perform this function on this vector so as to store the next derivative of each polynomial. We can differentiate a polynomial this way hundreds of times. Now to put a value into the last column. This will either be the square root of the eigenvalue or one of the derivatives of the square root of this value. Then we'll increment the row index variable here for each time we go around in this loop. So now we have the augmented matrix that we want to solve. We'll reduce it to reduced row echelon form here so as to get the solution. We'll store the degree of this polynomial here. Then we'll load the last column of this matrix into the polynomial. So now we have the square root polynomial. We'll have to make up a copying function so that we can compare two matrices for equality later. We'll copy the number of rows and columns. Then we'll copy all of the elements. This can be done quickly with one loop. Now we need to be able to evaluate the value of this polynomial for a matrix. We'll declare the function here. We'll load in the degree or length of the polynomial. We'll load in all three of the matrix dimensions here. We'll need 3 matrices to do this calculation. We'll set both of these matrices to be the 0 matrix. C is an accumulated value and must be set to 0 to begin with. B will be the identity matrix, and it's faster to set it to be 0 first. Then we'll set all of the diagonal elements of B to be 1, so now B is the identity matrix. We'll make up a loop to work through the entire polynomial. We'll add each term of the polynomial to the matrix C here. C should eventually be the answer. We'll multiply A by B so that B will represent each power of A in the polynomial. We can test this function later by adding 1 to one of its elements, making it definitely not equal to the square root. We'll put this comment in at the end saying that C is equal to P applied to A. This is the squaring function of a matrix, which should reverse the square root function applied to a matrix. We'll set these internal variables here. This is a multiplication function, but it's a matrix multiplied by itself. We'll insert the answer into matrix A at each location in A. We'll round it to the nearest millionth first, and then we'll store this value in A. Now to create a function that can make a matrix from Jordan blocks, which we'll need so that we can test this program properly. We'll set these row and column variables. We'll reset A to 0 because most elements will be 0, especially if A is large. We'll make up a loop to look at each of the Jordan blocks. We'll get all of these elements from the table. This loop makes up the Jordan block. We'll put the eigenvalue into each location in the diagonal. Then we'll get the location next to it. And if it isn't the last diagonal element in the Jordan block, then we'll put a 1 next to it. And then finally we'll increment this row indexing variable. Now to put it all together, we'll declare this function test4. We'll make up the square root table for finding all of the derivatives of the square root function. We'll make up a loop to test 100 random matrices. I tried it for 10,000 matrices. JavaScript is extremely fast and able to do this quickly, but only do it this many times if it's error-free. We'll make up tables of random Jordan blocks. Then we'll get the square root polynomial given by this function called interpolate. We'll get the matrix that these Jordan blocks represent. We'll copy this matrix to E to compare it later. We'll apply the polynomial to matrix A. The answer will be in matrix C. Then we'll get the square of C and place it back into matrix A. We'll check if A and E are equal, and if they aren't, then we'll print out an error and show all of these values of these matrices to help debug this program. And after having completed this test, we'll display this finished message here. And finally, here are some other Jordan block creation functions that can help to test this code. The one at the top can create a matrix with one giant Jordan block, which is good for testing this code, since it should in theory work with conjugated matrices if it can be shown to work with unconjugated Jordan matrices. I'm going to prove it more formally in a future video since it seemed to be too much to put into one video. So I hope that you have found this video to be helpful and interesting. Please click like and subscribe if you did. Feel free to share this video. Please leave some helpful thoughts in the comments if you have any, and thanks a lot for watching.